我听到都，听到什么？听到什么？哦。一个对一个等比。你听过吗？有那个有听过，那个有听过。嗯，麻辣烫哪里的麻辣烫？哦，麻油锅，切，OK。他们自己打包来的，他们打包来哦。他也是抓蛮多大。翻考卷过来。他们今天有林俊杰的陪伴，陪伴。三个三个。Okay. So today no quiz. And then I think we need to extend Simon as well. Yeah. So when do you want to submit? 啊？下个时间你明年再见咯。so 几时要 submit？下周二，下周二，下周二。OK OK OK，可以。Actually，我们差不多 cover 完了，要 cover 完了，里面要用那种算是 cover 完了啊，就是，但是我们还会再讲多一点点。All right. So I think we need to recall a little bit something from lecture 17. Okay. About relative. Okay. About reduce relative. Is this so Hn tilde of xa? So what's this thing here? Okay. So to look at a reduced relative homology, the setup was. So the setup is you have the short exact sequence of a relative chain like this. Okay. And then so where is the reduced part? So we need to first reduce the A and X chain. Okay, so what do I mean by that? So if I stop at C0, right? What we do for reduced chain was we attach a Z like this. Okay, we attach a Z like that. So what's the homomorphism here, or the boundary map, is to just add up all the coefficient. Okay. Then you might ask the question, what's this relative chain here? Okay, so what's this relative chain here? Okay, not that this extra part here is C minus, right? C minus A and C minus 1 X, right? So the reduced part, I mean the relative part is also C minus 1 X over C0 X. So that's why on this part here, you get Z over Z, and then this is 0 actually. Okay. What? 右边 maybe need one more 0. Like that. Okay. So what's the -1 chain here? I mean, short as a sequence here. So it is the identity here. It does make sense. So if you include the chain in A with the chain in X, right, it's just the same chain, and then you compute the coefficient. The coefficient on the left is the same. So it's the same map. The same okay. So it is the identity. And then it will make sense of this show the sequence as well. Because because what? Because this part is also identity, right? So this part is what's this map? It's an identity map. So this two compose to zero because you mod up the C minus one. So here it's a C minus one, not C zero. You mod something inside C minus one. Okay, so this is the reduced relative homology. This is the short exact sequence of complex for reduced relative homology. Okay. So in this case, you can see that it is the same chain. Okay, so if A is non-empty, then this Z will stay there, and then hash n x a tilde is just hash n tilde. Okay, so 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 the moral of the story is, if you look at the reduced relative homology, it is the relative homology. Okay, so you put tilde, don't put tilde on relative is the same thing. Okay, because in the end, the reduced chain for your relative chain is zero. Okay, the C minus one term is zero. Okay, you put nothing, you augment nothing to it. Okay. Another thing was, what if A is a point? Okay, another thing is, what if A is a point? So what is the relative homology for this part here? So what is this thing? Okay. I think the claim is, this is the reduced homology. So is it easy to see why? Okay, is it easy to see why? Well, you look at the, so the proof is, look at the long exact sequence of the pair xn, this point here, so x naught. Okay, not the just the long exact sequence, but the reduced version that we discussed just now, the reduced version. Okay, so if we have the reduced version, what do we have? It's like hash n of this point set here going into hash n of x, and then going into hash n of x, not tilde like that, right? But tilde is the same as without tilde, just now we discussed already. Okay. And then you can keep go on. Okay, you can keep go on until hash zero part, maybe. Maybe I'll write one more hash n minus one. Okay, and then you go to where, go to maybe hash zero x naught tilde, and then hash zero of x, and then hash one of hash one. No, H0 again. H0 point. And then I put a H minus 1. Do that like that. Okay. So what can you see? Because the reduced homology of a point is always 0. Okay. So you can see that these two terms are squeezed between 2, 0. So they are isomorphic. Okay. So this is one way to get reduced homology, is to take the relative homology against a point. Okay. This is one way to get reduced. Does it make sense? Make sense? Question? Okay. So far. Okay, if that's okay, let's resume discuss what we had the last lecture. So for good pairs, okay, we say that the map Q from XA to the quotient X over A over A. Okay. So you should note that this A over A is a point, no? Use of morphism, okay, on okay, since A over A is a point, so this relative homology actually is the reduced homology. Okay or not? Oh, and okay, so this is one way to find this relative, is to look at the reduced homology of the quotient space. This is like how we view things last time. You still remember when we try to compute the relative homology, but kind of like taking a quotient by A. Okay, if you still remember the example we start last Monday, I figured out already, or Gemini helped me to figure out. Okay, but the idea is similar to what Eric say. Is to look at the line that okay, you retrace. You can yeah, you retrace. Is it? Yeah, this example. Okay. 你怎么招生做那个钉呢？所以这样可怜哦，招生，所以这样可怜。坐过来，我没有欺负你啊，你坐过来。都坐在钉后面。嗯。Okay, so yeah, so last time we was like thinking, where's the hole? Where's the hole? Where can I see the hole? Okay, where we can see the hole? Okay, so one way to see the hole is we prove that this thing is not contractible. Okay, this space is not contractible, so there is something that's not a there's a proper loop. Okay, but at least we show that it's not contractible. Okay, so how to show that it's not contractible? Basically, is you look at your R2, right? Okay, look at your R2, and then you have do this, right? B1, B2, and then you look at a line that join these two. Okay, then you can retract everything to this dumbbell shape here. Okay, and then you do quotient. Okay, so you if in that case, after you do quotient, then deformation retract to S1. Okay. This case here, you do retraction, you do deformation. It's a retraction. So retraction is going from type 1 of that thing, the quotients of R2 by P1 to type 1 of that one. Okay. But last time you proved that inclusion is injective, right? the induced by the inclusion is injective. But what's the inverse? The inverse is R star, right? R star is the induced retraction. So meaning the induced retraction should be surjective. Okay. So you surject to something non-trivial. Okay, so your pi 1 is non-zero, so you have not. Okay. So you are not, your pi 1 is not equal to something that's contractible, so you are not contractible. But then yesterday or the day on Monday, we proved that this is the basis can generate. Yeah. Okay. So I put it in the notes already. You can have a look. Hey, where is it? Yeah. Okay. This thing. So we promised to prove this. Okay. So to prove this, we need the good pair condition to help us. Okay. Later we'll see how it helps us. So since it is a good pair, right? So let V such that I don't want to write words. I draw it. So here got X, here got A. Okay. V is the neighborhood that deformation retrace to A. Okay. Make sense? Okay. So then we will use this commutative diagram. So we'll explain this commutative diagram and then explain the isomorphism. So there are two cubes happening here. Maybe you can try and see where these arrow come from. Try and guess or try and think about it. This arrow come from. This cube here or sometime and then try and see where they come from. Okay, so the hint is this picture here. So the hint is this picture. Okay, you need to consider the long exact sequence coming from the triple. Okay. Still remember a long exact sequence coming from the triple? So what's the triple here? So the triple, the chain complex that you need to think about is Cn of VA going to Cn of X. I think it's the second isomorphism theorem. XV, yeah. And then going to Cn of XA. Let's see correct or not. So second isomorphism theorem is like the fraction you learn in high school, right? X over A is equal to X over V over V over A. Correct or not? Mm. Did I make something wrong? Mm. Mm. Wrong. Seems like wrong. So how to fix it? Mm. I think should be a V here. Here is the A. Okay, so this is the chain we're gonna get. So here is V. Yes. Okay. Make sense? Make sense or not? Okay. 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 So if you have this chain, right, then this is the upper part, upper left part here. This is coming from the long exact sequence of this thing. Okay? Because you are squeezed by Hn of VA and Hn of V, Hn minus 1. Okay, then that two term should be zero. Be zero. Make sense or not? Because V deformation retract to A. So your chain complex is CNA over CNA. So it's zero. Okay, so that's mean this part is an isomorphism. Okay, so this is coming from LES of maybe I name this one of one. Okay, this arrow here. What else you know? What else you know? What else you know? What else you know? Excision, right? Do we have excision here? Or which one is easier? Uh, which one you want? Which arrow you want to look at? 右边 top. Okay, so look at this, right? This one, right? Okay, this is what is this? This is coming from excision, right? Eh, so does excision give you isomorphism? Last time, what did we say about excision last time? So let's recall the excision theorem. Okay, so excision also induces an isomorphism. Okay, so if you take away that here, okay, our group pair will satisfy this condition. Yeah. So you can your homology before taking away that we will say as after the group pair. Yes. Sorry. Third or second? Oh, it's third. Okay. Always confused. I don't know. The normal thing. Okay. So this is the third isomorphism theorem. So did I label the wrong thing inside my notes? Maybe I need to check. Okay. So top and bottom are isomorphic by excision. Okay, because you take away a nice subspace. Okay. Hey, where's our goal actually in this picture? Did you realize where is our goal? Where's our goal? What arrow we wanted to do? You recognize which arrow we want? We want the first vertical arrow, right? This is our goal. Our goal is here. Isomorphic here. Okay. So if I want isomorphic, then it should be the composer of like other isomorphic, right? Well, first of all, you need to prove that this is commutative. You need to prove that it's commutative. Should be. I don't know it's how obvious it is, but should be workable. After you commutative, then you prove that the rest of the should be isomorphic. Okay, so in particular, this three map will be isomorphic. To prove that this three map isomorphic, why we need this? Obviously, there's some map we cannot say that it's isomorphic, so we need the help of the other. Okay, so in particular, this one we need help. Okay, this one we are not sure. Okay, this one we are sure actually. This one is obvious, right? Because this is actually the same thing. Because V deformator retract to H. Yeah, okay. So the chain complex that you consider should be the having the same homology. Okay, so this part is deformation retract. Okay, so感觉好像，等下我想一下啊，上面那个也可以过。I think 跟上面是一样的东西，跟上面是一样的。 跟上面是一样，so yeah，只是 yeah 跟上面是一样，yeah 跟上面一样。OK，what things I need to say？Okay, so our final thing to show as isomorphic actually is last one here. But it's not that this third one is easier to define. So what's wrong here? Well, the point you want to use here is actually Q is homeomorphic. Q is a homomorphism in this pair. Why it works? Do you know why? Q is a homomorphism in this pair here. Q restrict to a homeomorphism here. So what is Q? So Q is a map that map X to X over A and then A to A over A. Well, this is the quotient map. Okay. The claim is if you just restrict, if you don't look at A, then it is a homeomorphism. This is bijective. Does it make sense? This is quotient map, right? So you quotient things together outside the thing that you quotient gets sent to the same place. So it's a homeomorphism. So this is how you get the last isomorphism here. So in this case, although the arrow here is like going against each other, but because it's the isomorphism, so you can build the rope going to the other side. And 好用吗？isomorphism 有 inverse OK。Question? Any question? So 这个 this kind of inverse is very important. In a higher algebra course, right, we call somehow we call this thing a section. Very important. Okay. Right. Are we done? Yeah. So here we are done. Any questions so far? Hey, later please come and look at your quiz. Look at you. My calculus, one student very out there. 很可爱，应该不叫 Q 吧？都是 Q 的意思，就是很 lovely，应该讲很 lovely，就是来，他考完试过后，我讲我没有，还没有，不至于，没有。我讲，我们不仅他一直要问我问题，刚刚讲过，我讲不紧，我们等下会讨论，我们泡一下讨论。老师不要快回来，快回来，我不要讨论。我讲，你要看看你哪里错，然后你要学哪里要改。对，不要太热不要讨论。然后他又当下又很想问我，我又想问我的答案了。我都忘记了题目了。OK， 很搞笑啊。Alright. So before we continue, have we introduced mapping con last time? 我们有讨论过还是没有 ？CW complex 我没有介绍过，没有。OK， 好 ，Never mind. We just start a new part. So let 我们有 mapping cylinder 对吗？没有 mapping con 吧 ？OK。上面有 mapping torus 对啊，但是就没有 mapping con 是不是？OK， 好，那我们先到 mapping con。Actually， 我不知道，好像课本是介绍 mapping con I forgot 了，忘记了，没事。So let F be a continuous map. We'll define a mapping con or the mapping con. Okay, is CF. So what's this CF here? Okay, let's write down the algebraic notation first, and then I draw it for you. So what you do was, so I need to tell you what CX on. So CX is the con. Mm, uh, well, okay. So I think I tell you what is con. I didn't tell you what's a mapping con. Okay. So what we do was we take an X. Sorry, we take a Y. Okay. And then we take an X like that, X and Y. And then X map to Y. So maybe map do something like that. Okay. X cross 1 timeline. But at the X cross 0 timeline, right, we identified it. So this is the X cross 1 timeline. Okay, we identified it. So this is a mapping con. Can you see the con? 有点像被砸烂的 vanilla sundae con 啊？什么 ？Yes, actually it's X, but we identify X.
我拿破圈掉，
对，有破圈掉。对，是 X 是 X 来的，每一层都是 X 来的。
所以就变成那个两层。
Yes，没有错。
然后画点点。
没有吗？我把我时间推前位。Why is it destroy? Okay, so this is not quite a destroy union. I remember when we introduced this notation, right? This is like how we do it. We do it against way. It's not just 不是那个只有那个嘛，我是有一个那个，懂没错？啊，这个跟 destroy union 的 notation，因为 union 没有这个 f 不一样的，就是什么这个意思就是 OK。The meaning of this is OK. I should write it down. 我有画在上面啊，但是我要写，我应该写出来。So yeah, 对 attachment. So what we do is we attach, attach this to y. This 就是 CF 啊，along x cross 1. So how to attach? Via x1 into fx. That's it. Yeah. So far, okay. So far, so good. Okay. So what is the relation between this and the mapping cylinder? Then? It's just without the quotient. Okay, so if you take the mapping cylinder and then you starting part, then become tom. If not, it's a cylinder, 对吧 ？cylinder 或者你把它包起来就变 tom，对不对 ？cylinder 是不是有洞？你试下，你去美国呢买一个3D，直接把下面咬掉，弄出来。3D con
你知道你会出现吗？
啊？1块钱还要我出？OK，it's OK。OK，好，Yeah，I think example 可以 skip 你们是很聪明的。没有了，我就是要 skip 吧。Example, I think we can skip unless we want to use it, then I will introduce again. Okay. So let's get a proposition. So let's give a pair again. No need to be good pair or what, just a pair. Then what we have is for every n. Maybe you can spend time thinking about this a little bit. We can discuss. Okay, so the relative the mapping How is this a mapping corner? So instead of F, I put an A here. What does it mean? Can you guess what it means? This F become A. So what kind of map is mapping to A? Mapping A to A. Inclusion. You cannot say identity because your X could be larger. So it is always an inclusion. Identity is also an inclusion. Okay, it's an inclusion map. So it's a mapping corner of the inclusion map. 可以想象那个图片吗？图片是一模一样的，图片是一模一样的，就是你把那个 x 想成 a 就好，可能一个 subset of y 就好。OK， 可以想象吗 ？Relative homology，OK，is the reduced homology of 这个。不小心跌下去的3的。为什么？啊，要我亲手叼一个蜜雪的蛋糕给你？你等下解释这样有什么关系？
你的地方很丑啊！
我要表演给你看一次吊雪糕的样子。对呀、不类似呢？
类似的，
啊？
非常类似，好不好？
你真的是没有生活，我也没有生活啊，你比我更没有生活。
不要给我口
不要浪费钱。OK， 好，应该抖音有很多影片可以找的。呀，对对，哎，good good 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 good，就这样嘛，对吗？我知道了，我知道为什么他不知道。你知道他每次吃的 ice cream 是 Baskin Robbins 来的，所以他是 mapping cylinder 来的。他是 mapping cylinder，他不是 mapping con。难怪你不知道，太有钱了。Okay. Okay, so how to show this? Yeah, how to show this? Using what we have learned. Okay, so well, this kind of proof, right? Definitely you need to start from somewhere. Maybe you start on the right hand side. Okay, and then we can go from reduced homology to relative, right? Can we? Do we have this isomorphism here? Is this what we have done just now? 加东西啊。Wait, let me check. Am I right? What am I doing here? 看一下 What am I using here? 周末我可以直接加一个逗号进去。我是不是漏了什么？想想看，周末可以加哈。OK，不然先一讲加了过后会发生什么事情，要不要？那我们再想一下可以加吗？还是中间要加吗？Well, okay, this one, let's black box first. Later we want to figure out. So if this happens, you can do excision. Okay, so meaning you take away a point where this point is the tips of CA. Okay. 啊 tips 啊 tips 是什么？这个点是 P. Okay. Then if you take this away, then everything can deformation retract down to X and A. Okay, so excision and then deformation retract. Okay, so now the story what happened here. what happened here. Definitely, we need to use what we have introduced. Definitely is using what we have proven. So why? Ah, 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 ah. Hey, hey. If I want to just use this, okay, if I just use this, okay, if I just use this one, right? What do I get? Yeah, maybe I copy paste first. Let's try. I forgot already and I didn't write down, so this is the problem. Okay, so if I use this, what happened here? This one bring down. This one bring down. And then this one put it here. Okay, if this is true, then I will put isomorphism like Hn of. So I would backward, backward, then I get Hn tilde of x on a Ca on Ca. Oh, is this two thing the same thing? Seems like not. Yes or no? Is Ca contractible? It cannot be, right? E. I didn't copy wrong anything. Is this statement correct? The con ah a con the con of a space is always contractible, right? Did we prove this? Like it should be, right, because it is isomorphic. I mean homeomorphic to a disk. This did we prove something about con? Mapping con. Let's see. So con. 我觉得我们有 prove 了一些特性。哦，没有，只介绍了。Con is con contractible. Con is contractible, right? Because you cross I is that interval, ma. And interval, all the line interval point. So that line you contract to the tips. Doesn't make sense. So if you have x, right, and then you all of them have a line, right, cross I, and then you join them at the slice 0. So this is the deformation restrict to a tips one. Correct or not? Every point get a line. So you are portioning out by a point. So as if the same thing, no? Does it make sense? You portion out by the point. Does it make sense? Does it make sense? without that look like this. Well, my point is, I guess this thing is isomorphic to HN to the X union A of the CA over a point like that. Then this thing is the same we started with. So basically, you are quotient out the tips on it. So you have the whole thing, and then you quotient out by this point here. Then this point is still that point. This is still the same point. Maybe this is I write P here. Make sense? Does it make sense? Homotopy equivalence. Yeah.哪个 step 有问题？有问题吗？没有，没有，有的话 OK 啊。我们拿去问杰们来，没有，我们要请一个杰们来上课就好。没有，有时候没有，我们要教你们讲辨别杰们来。啊，考试可以用啊。Gemini 下面有一个 disclaimer，Gemini sometimes make mistake 啊，这个也是 OK，good，很好。OK， yeah， I think maybe it's a good time we can break here. It was super. Oh, we got a new deadline for assignment next Tuesday. Oh, if you decide your project topic, you can tell me. So Eric decided already. If can, we try not to repeat, sir. Okay. So he picked the Adam spectral sequence. Okay, so you can pick another one. Hmm.
因为我很累，
今天怎么很累？
我早上在考 A，他们说他 I 只有20分，
20分
不会的
啊
，100分我就20分不会。
我靠！
他已经帮我语懂，现在就先全部的 advice 了。我是有点不舒服。
後天有去，後天有拿嗎？後天有考。OK。OK，我觉得我懂了。I think 没有这么复杂，我们不可以这样子做，我觉得，因为它是在 denominator，有点恐怖，应该不可以这样做。嗯，这个我觉得这个是有问题的这个 part。OK，this part I think got something a problem here. I think you cannot use the deformation retract in the quotient. Not supposed to use in the quotient. 就有一点你在乱约那个 denominator 的感觉，就是感觉your deformation retract should be applied to the whole space, not the quotient part. But the point here is this thing is contractible, so this is the point, so it's enough already, I guess. Yeah. You don't need to really deal with the quotient space, but you deal with the quotient chain, relative chain. Okay, you deal with the quotient chain. So I guess what you should really need is this thing. Okay, what you really need is this thing. Okay, and then what things do you get? Should I write it out? 写一下啦，写写看。我好像也从来没有写过。Okay, and then we know that. What do we know? So we have the right, the real chain. So this one induce a long exact sequence on homology could be reduced as well. Reduce. Yeah. Okay, so this one is the look at the reduced form. Okay, so we get CA and then going to hash n of x union CA and then going to hash n of x union CA, comma CA like that. Okay, but when we say that CA is contractible, that means that which term disappear? Which term disappear? The homology of CA will disappear. So that's why you get a isomorphism here, if we consider the reduced one. Okay, so this is it's not the deformation retract reduce isomorphism of homology, but it helps you to simplify your log analysis. We apply the deformation retract on CA only, not on the quotient space. That one is very horrible. OK 吗？有问题吗？有问题吗？OK，刚才那个我觉得是错的，不可以讲。下面是那个 deformation retract，肯定会有 counter example。把这个是 OK 的，因为 because you are just calculating what's the homology of CA. But CA is contractible, so it is the reduced homology. OK， 这样了。So I think 这几天或者这几次 lecture 下来都是 short as a sequence，然后过后有一个 long as a sequence，所以这个过程你要熟悉一下。Okay, I guess we can continue. Okay, let's continue. So last time, when we still remember when we discussed Sn, and this is x3, right? We draw a CW complex like, is it like this? Or something like this? Using simplex 哪个环线 is how to say? If you use two tetrahedron to build this S, this is S2. Build this S2, right? Let me tell you, delta hedron is delta 3. Okay, so if you use two delta 3 to build this S2, right, you will have an extra layer, which is not S2 anymore. So when we draw this, what we meant is we put 6 delta 2 together. Actually, it's a 6 delta 2 才 make sense. 为什么看出来？等一下我们要用到它的 CW structure，我怕我上次好像也有这样想过，但是我不知道有没有讲出来，可能我有讲出来。但是我讲 tetrahedron，但是 but it's wrong, you cannot use two tetrahedron to build S2 because you build an extra layer. Okay, instead you should use so which is 6 delta 2. But how to use 2 delta 2 to build S2? Yeah. So how do you use 2 delta 2 to build S2? Yeah, 不需要充气，它自动有气啊，就是把它边连起来吧。Okay, just glue their boundary together. Okay, just glue their boundary together. That's it. Okay, because this is topologically a this. Okay, this is topologically a this like that. 就这样吧。Okay, topologically a this. Okay, 明白吗？家里有没有百家被？就是用那种碎布缝起来的。哦，有这呀啊？哇，有没有照片？有照片，上网找一下。哎呀，这个没有见过，你们那里没有这个东西哈？OK，可能是南部人的东西，南方人。好，OK，这个有看过吗？没有折过吗？这个背啊，然后就用不同的 square 来把它变成一个大 square。Okay, so yeah. Okay. Well, I mean, you can think of the boundary as this side, right? Also can 1, 2, 3 like that. Okay, so here, here, and then here. Okay, so you can think of the boundary as a equator. Okay, so the hemisphere are the delta 2 simplex. Okay, so this is the motivation for next part. Huh? Huh? Use homeomorphism. So need to okay, first of all, you need to parameterize them first. After parameterizing, then you need to send the site to the boundary, and then maybe you need stereographic projection. No need, no need. How? How about you if you draw circle? 啊，对对，我就是要算这个，我就要画这个东西啊。 可是你 inscribe 外面或里面有差没？哎，你 inscribe 了过后呢，你要解释什么？You have a dilation 啊。我就是那个 calculus for 这种哦，but I mean 应该有 exist 这样的 map 吧？有吗？应该要有啊。I mean make sense 嘛，因为这样的 map 嘛，x2 就是把一个条线把它变歪，就是来把这里你要来有一点可以吗？这不是差不多出的东西了。好，这个哎，这是 calculus two 不是 calculus two，你还记得吗？我们 rectangle 啊，把它变成圆的来 integrate 啊，然后那个换 multiple integral 的东西，我没有印象。multiple integral，你要 domain，有时候是 spherical 啊，有时候是 spherical 或者是 spherical 啊，spherical coordinate 啊，spherical coordinate 开始的地方就是 R3 啊，然后它是用那个什么 rho sin theta 什么，R z 不个啊，还是什么？没有教也忘记了，那是什么？就是那个 rho sin phi 跟 cos theta 那个就是把你的 R3 变弯呢啊，你要这样子的东西把你变弯。这个 polar coordinate 啊，I guess。为什么变弯？是变弯，真的是变弯，真的是变弯。因为如果你去拿一个 square 的domain 啊，然后你 apply cosine theta cos phi 这个，你 coordinate 出来它就是一个圆的东西，它是方。然后如果你去算它的可微来，就是什么螺旋之类啊，真的是有可微圈在那边啊，它真的是变那些东西就是需要用到，可以去找的。OK，I think it's polar coordinate 啊，如果没有记错啊。但是 polar I guess 是从这个 polar 是从 polar coordinate 应该是会从这个去到这一个，但是现在你是 triangle，所以你要改装一下吧，I guess。OK，跑哪里去啊？OK，let's quickly continue。OK，我们要不要花时间在这里呢？要还是不要？我们来得及吗？OK，maybe 我们就 discuss 啊，不要 go through details. The details is in the lecture notes. So maybe let's look at this. What is the relative homology of this quotient out by the boundary? Okay, just now, by what we have learned, right? This is a reduced homology of dn over boundary of dn. Sorry. Then this is just Sn. Okay. But the problem here is who is the generator? Because we know about H and Sn, right? The reduced homology of Sn, H and Sn, we last time we proved that it's Z. So there's one generator. So who is the infinite cyclic generator? Okay, so who is that generator? What do you think? What do you think? Huh? So who is the generator here? What's the generator here? Huh? What do you think? What's the generator here? What's the generator? Well, the generator is the obvious one. For example, if x1, right? So what's the generator of h1, x1? Is that circle? That's the generator. If S2 is the two cell that bound together, that's the generator. But how do you describe that? Okay, so there's an easy way to describe that is you build your xn using two delta, okay, delta n1 and delta n2, okay, it's like what we do just now, okay, glue along the boundary. Then the generator is delta 1n minus delta 2n. Okay, is that whole thing? Okay. So the gluing process here become the sign. Okay, the gluing process here become the sign. Does it make sense? But how to prove it? Okay, how to prove it? Maybe you need some description from the relative homology. Okay, so maybe I can tell something here. This relative homology here, right? This thing here is generated by the identity map. Because not that, this H here is a singular homology. Okay, singular homology. Maybe you might think weird, oh, why don't I put dn here? Because dn and delta n is topologically equivalent, homomorphic. Okay. 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 So actually, we know more than that is dn, comma, del dn actually is homotopy equivalent or homeomorphic, actually homeomorphic to delta n, comma, delta n, like that. Why is this a cycle? Is it clear that why is this a cycle? So meaning in that relative chain, why this one evaluate to 0? So you have this identity map, right? You apply, what do you get? You remember how to apply the boundary map? You restrict your map to every faces. So if you restrict your map to every faces, what do you get? You just get faces. But in the next level, what do you do here? You quotient out all the next faces. Correct or not? I want to write it down. Let's write it down the chain here. So here is Cn, right? Cn dn over Cn del dn. And then the next part is Cn minus 1 dn. And then Cn minus 1 of del dn. Okay? So you quotient out the n minus 1 faces here. And so it is in the cycle. This thing is in the cycle. What else we need to check? Then you need to prove y is equal. Okay, this part. You look at the notes. Okay, any questions so far? Any questions so far? 有问题吗？有问题吗？有问题吗？没有。Okay. Yeah. So I mean, there's work here. So there's some work here. Okay. So there's some work here that you can have a look. Okay. Let's go to the next part. Okay, so the next part is we we do excision on CW complex. So as long as you are CW complex, if you have two subcomplex, then you have this excision property here. Okay, so because CW pairs are good pairs, you can deformation along your skeleton, and then you can apply excision. And then this wedge sum I think is important for your assignment. So if you have a wedge sum of topological space, okay, what is the reduced homology of wedge sum? Actually is the direct sum of all the topology. Is this hard to imagine or not? Hard to imagine. Okay, so maybe you need to think about the pair here. So what's the pair you need to think about? You need to think about the topological space with the base point. Okay, with the base point. This is the pair you need to think about. Okay. And then you will have this chain of isomorphism. Because how you take a wedge sum, you take a disjoint union and then you quotient out the point that you want to do with it. So this quotient, this you get this wedge sum. Okay. But then this is a disjoint union, right? You want a map that go out from a disjoint union, meaning you want a map that go out from every space. So this is how you go between disjoint unions and direct. And then this become a homology, a relative homology against a point. Or again, we have a reduced. Okay, makes sense? Good. So this is very important. This is one of the homology axiom. If you want to have some homology theory to work, the homology on the direct sum must work in this way. This is one of the axiom of homology. Okay. So whenever you see homology on wedge sum, it should decompose into direct sum on the module space. Good? Oh, good. Very good. 有问题吗？ Have we computed homology of torus before? Did you know homology of torus already? Or just know about pi 1? Don't know yet. Okay, in that case, we should do that. Yeah, let's do the reduced homology of torus. X1 cross X1. Okay, let's do this. Hey, how to do this? Yay, use whatever we have learned down. So can you think of what's the relation about why we want to introduce wedge first, and then do this X1 wedge S1 thing? Cross X1. Can you think of a relation? Why we want to do wedge first? Why we want to go wedge first? Multiply thing. What's the relation between X1 wedge S1 and S1 cross X1? Torus.不算 torus 哦，那个Yeah. So it's the skeleton, right? So it's the first one skeleton of T. So 现在我们就是要切一个洞。Okay, we want to use excision. So 我们要切什么洞呢？随便一个洞，非常好，就是随便一个洞。我们很随意。OK， 所以我们先画一下这个，头的水。非常好。对，我们就随便画个洞。OK，how about 我们用这个 presentation 会比较好，这样大概就知道切什么地方。没有打叉，对不对？应该是一样方向。OK，so we 切一个洞 ，so we one close disk here. Okay, with some epsilon radius, not very important. So this is Z. Okay, and then this is our T. And we need a slightly larger space that deformation restrict to it. So maybe A is a larger circle like that. Okay. So that we have this condition Z bar living inside interior of A. Okay. So that such that we can compute. So this is my addition. We have Hn of T minus Z, A minus Z, isomorphic to Hn of T. Okay. So the point here is 上次我们有讲过嘛，那我们打这个东西，这个 case 就是这个情况。And because it deformation retract to to x1 with s1. Okay. So what else we need to care about? So first thing first. Okay, since A is contractible. Okay, 用我们刚才 use the long exact sequence just now. We have this relative homology actually is the reduced homology of T. Okay, so this is one way to find reduced homology of the space if you consider the relative with some contractible space. Okay, so that is squeezed between. So this comes from a long exact sequence, right? So let's write down the long exact sequence. So here is Hn of A, and then here is Hn minus 1 of A, and then this go to 0. A is the disk, another disk, a larger disk, 2 epsilon disk that bound this epsilon disk Z. Okay, contractible. Okay. Right. Okay. How much do you know about T minus Z and A minus Z? T minus Z, you know, right? Is S1 with S1. A minus Z is an annulus. Okay, which deformation retract to a X1. Okay, good. Yeah. So second, T minus Z deformation retract to homotopy equivalent to X1 with S1, A minus Z S1. Okay, so in that case, look at the LES of T minus Z and A minus Z. Okay, so what's this LES here? Maybe the interesting part is just at the bottom. So let's start. Because what's this zero term here? Can you revive this zero term? This is H1 of H2, sorry, H2 of T minus Z. T minus Z. Yeah. Yeah. T minus Z. Okay. So why is it 0? Maybe I can tell you. Or can you tell me? Can you tell me why? Tell me why. So another 0 happening here is H 算一下22110. So this is H0x1. 对呀，对，哎，错啊，对，这个 ，OK, good. So, first 0, why is it 0? So, first thing is H2 of T minus Z, which is equal or isomorphic to H2 of X1 with S1. Just now we said that it deformation retract to its one 11. But H2 is also isomorphic to the reduced homology, right? Okay. Then just now we proved that reduced homology on direct sum is direct sum. Okay, so it is a direct sum of x1 plus h2 of x1. Is it a homology or reduced? Let's check. So how do we split? Is reduced, reduced. Okay. So 0 plus 0, okay, because only hn xn is non-zero. Hn tilde hxn is non-zero, so 0 plus 0 is 0. Okay. What else we want to know? What else we want to know? Why do I put a h0 x1 there? Why is it a 0 there? Why is this the 0? Okay, maybe we can figure out later. But most importantly, what's this map here? What's the map here? Okay, so let's look at this map first. So what's this map? Do you know what's this map? What's this map doing? So S1 is the circle. So okay, let's draw it. So S1, the first X1 here is the deformation retract circle X1. Okay. You want to go to X1 wedge X1. So it's this outside here. Okay. So what did you do actually? So you deformation retract this circle to the deformation point. This whole circle here. What's this whole circle here? What's this whole circle here? So first you take the generator. Okay, you map it to the generator in X1 wedge X1. So what's the generator here? So what's the two Z here? One corresponds to A, the other corresponds to B. Okay, but how do you glue them? How do you glue them? A inverse, B inverse. What? So let's say A is 1, 0. A inverse become negative 1, 0. B is another generator, right? 0, 1. And then the other is negative 0, 1. So you glue to this linear combination. 0. So it's a 0 map. Okay, so here actually is a 0 map. Okay, so we done this. Okay, so are we enough to compute now? So, so, since this is a 0 map, since this is a 0 map, and then this is exact, right? So this is isomorphic. Wait, let me see. Okay, so since it's a 0 map, then we should be able to compute now. So let's compute it. Okay, so let's compute it. Right. So I claim that it's enough to compute. Let's see enough or not. So what do we want to know about? This one. Okay. So instead of hn tilde, right, we can compute h0t also. So h0t is the number of half connected component, right? Okay, so here is that. Or do you want to compute from the start here? You want to compute from the start here? So if we compute from the start, what do we see? So if you put a 0 here, you put a 0, and then so what's this thing here? Okay, here's 0 of t minus z. We didn't quite write it out right. Not yet. Should we do that? Or you are happy with counting path connected component? You want to use the long exact sequence to compute it? Or maybe we can put it as an exercise first. If we got time, we can do it. If no time, I try and do in the notes. Okay, how about H1T? Okay, so H1T is the reduced one. Why we like the reduced one? Because we like to relate it back to the relative homology. Why we want to look at the the relative homology? Because we want to use addition. Okay, and then if we use addition, then this is z plus z. Why is this z plus z? So let's look at here. So why is it here? So kernel this map is equal to the image of this map, and then the kernel the image of this map. So this kernel is 0. And then the kernel of this map is so the kernel of this map is everything. So everything is the image of this map. Okay, so it is injective and surjective. So we know this space, we also know this space. So this makes this very important. Why is this a 0? This makes this very important. Why is this a 0? Why is this a 0 map? This makes this very important. I think we need to do that. Why is it 0? 0 of x1. Are we considering? Okay. Okay. I think I know what's wrong here. I guess these are the reduced version. Okay, this should be the reduced version. So let's look at the reduced version. Okay, we should look at the reduced version. Okay, otherwise, H1 X1 won't be Z. H1 X1 should be Z plus Z. Reduced version. So reduced version only is that. So this is the reduced version. Okay, if it is reduced, then is it 0? Yeah, it is 0, right? Because H0 of X1 is 0. Because only Hn Xn reduces Z. Okay, for other n is 0. Does it make sense? For other i，有问题吗？我们要考虑的应该是 reduce the long as a sequence，不然的话，H1 S1 S1 应该。H1 S1 是什么？我们没有算过，我们只算过 H2 的 S1。H1 S1 会表达，我没有算过 H1 S1。Maybe 可以做一个exercise。What is X1？ H1 S1 也是。为什么会猜它 H0 S0 是2个 Z？ 对吗？所以我就猜 H1 S1 会比较大。But 我们没有算过，我们只有算过 H N2 的 Sn 用 induction。Maybe 我们可以算一下这个是什么东西。Okay, but anyway, if we continue, what is H2 here? Okay, again, isomorphic to the reduced homology, but reduced homology is equivalent to relative homology, and then it's equivalent to excision. Okay, so the excision of this part is Z. Okay, let's see why is it Z. Okay, so this is the thing we want. Okay, but we know that is the image of this map, which is 0. So it's injective. But the kernel of this map is the image of this map. Okay, so what does this mean? So the kernel in the image is everything. Okay, so it's injective and surjective. So it's surject onto the reduced homology of S1. First reduced homology of S1. So is that okay or not? Okay. So the moral of the story is we want to find the homology of a torus. What do? We make a hole. Okay, 我打破它。Okay, turns out that 我打破它跟没有打破它的 homology 是一样的。你看，看这边 excitation 有打动跟没有打动的 relative homology 是一样的。OK，但是打动的很好用，因为这个打动过后的这个 space 就是能够算出这些被打动的 space 是什么homology。make sense 吗？打动过后deformation retract 的 homology space 容易算，我们都算过了。上我算过了 ，HNS 我们也算过了。打动的我们不会算，但是打动过后deformation retract 都没有我们。
Insurance or what organizational violence on the
make sense. Make sense. 不会跑出两个 Z。make sense. OK， 因为如果假设我们是用那个 abelianization of pi one 的话来看的话，就是 pi one abelianize 过后就是 h one。So what is the pi one of x one？ 我们懂吗？因为它就是 z 嘛 ，abelianize z 就是 z 哦，还是 z。OK，so h one of x one 是 z 哦，它的 claim，yeah， 那个 abelian 那个呀，非常长的一个证明，但是很 intuitive， 非常 intuitive。因为什么？pi one 是个 loop，h one 是个 singular one simplex， 它就是一个 image， 所以那个 loop 是一个 image of 一个 map 嘛，对不对？就这样呀。loops 吗？我们讨论 loops 的时候，我们还是要 parameterize 它嘛。其实这个就是 simplex 的概念了 ，singular simplex 的概念。你要讨论一个 loop， 结果你要有一个 map， 但是这个就是 singular and simplex 的概念，你要有一个 map 来形容你怎样把这个 loop 放进去make sense 对吧？哦，这个洪瑞你看了吗？我看了忘记了，为什么有 abelianization 啊？是你的判吗？是你的判吗 ？abelianization 有看了吗？你看了吗？有没有看？我看了，我忘记了。它好像是关于说有一个 relation， 有一个 abelian 的 relation， 就是你记得吗？就是 like 会有一个 A inverse B inverse commutator 的 relation among 这个 loop 会有这个 commutator relation， 所以他把这个 commutator 切过后就是 abelian。OK， 有几个 technical 的 lemma， 然后那个 lemma 过后就是会是 abelianization。哦我不知道打了没有了，我还没有看你的那个 correction， 你可以等那个 exercise 做完再发给我，我可以先把你这个版本放上去，but 等你做完 exercise 我可以再看一轮。Larry 的 exercise 我还没有看呢，我可以相信你吗？ 还是有人看了吗？有 typo 啦。OK，argument 有问题吗？没有，你觉得 OK 啊？你 buy，你顶 OK，这样你 send 给他的 typo，你 send 给他。你的 week 7还没有给我。我想要，对，我想要试用它。嗯，非常好，暂时还挺不错，看看它什么时候。OK，嗯，what else 啊？OK，what else is there are few application that we do. Okay, what we can do was uh here. So if you look at two non-empty open set, right? If they are homeomorphic, then these two open set have to come from the same Euclidean space. Okay，强吗？这个 result 强不强？给我 update 一下，因为它有一点 OK，看一下这个 result 强不强？Non-empty open set 啊，比如说啊，你要拿一个圆圈，R2，要去 R1 open set 是一个 open interval，这两个有可能 homomorphic。如果它 homomorphic 的话，意思是说那个 Euclidean space 一定要是一样的 Euclidean topology，也是用 Euclidean topology。Okay? So homeomorphic open set must come from the same Euclidean space。合理吧？应该，因为 open interval 的 open 跟 open ball 的 open 就不太一样嘛，有方向，有来 more than 有 different direction。Okay, so let's see what is the argument here. So again, we use addition. Use addition here because we use the E against A intercept B, use a smaller open set. And then we look at the long measure sequence of this pair here, and let's see. Why we have this isomorphism? Because the contractible space become the 是另外一个变成 contractible，不是这个。Okay? So the isomorphism occurred at another just now 我们是 KK 嘛，对不对 ？NN 嘛，因为它是 n minus one，那一个是 contractible 嘛，这个是 OK。It's okay。如果我们有 what can we do next？So what's this space here? So RM 打一个洞 ，RM 有 contracted it's actually just Sn minus one. Okay. So if it's Sn minus one, we know very well what is this space here. It is Z if K equals to M because you need to match up with n minus one here, and it is zero otherwise. Okay, make sense? Okay. So if these two open sets are homeomorphic, meaning their homology have to be isomorphic, so they have to be happen the non-zero case at the same place. So let me go. Okay. Make sense? Okay. So this motivate one concept here is this hash n of x tangent against the tangent x is called the local homology group. And this is called a local homology group. Why is it local? So if you think about the proposition we had previously, this group is like homomorphic, isomorphic to reduce quotient by x minus x minus the point. Okay, so what is this? This is like just looking at that point. Okay, looking around at that point. And what's the homology at that point? So that's why we call it the local homology. is a homology acted. Okay. Yeah. So this homology groups can tell when the topological space are not locally okay at a certain. Okay, recall that it is not if and only if. So the relation between homomorphism is not if and only if. It's just one direction. So you only can say if they're not the same, they're homomorphic. You cannot say that, oh, if the H1 is the same, they are homomorphic. Cannot. Okay, you only can use contrapositive. You cannot use the, is it called the converse? Converse. Converse. You cannot use the converse, but you can use the contrapositive. Okay, so this is about local homology group. Next is simplicial singular. The equivalence between simplicial and singular homology. So we try to relate these two together. Once you can compute singular homology, it is the simplicial homology. Okay, so this is equivalent. We only show it on the delta complex, but this is enough for all the spaces we look at for now, at least. Okay, so on delta complex, these two things are the same. So to show that these two things is the same, there's a very technical lemma we need to have. Okay, I'm not going to do it in this class because it's just a routine diagram chasing. So what's the 5 lemma here? So 5 lemma here involve 5 terms. Like that, 2 exact rules. And then if you have A, beta, delta, epsilon, so the outer 2, the middle one has to be isomorphic. This is the content. Why? Diagram chase. Diagram chase, go and chase. Okay, so you need to prove that this one is zero actions, everything. Okay. Yeah. Okay, so you need to do these 2 things are very straightforward. Check it is subjective, check it is objective. Okay, but to do this, you need to do the diagram chasing. Okay. Okay. Yeah. So you need to do diagram chase. Okay, but this is the famous 5 lemma. Okay, this is one of the important tool in the subject of homological algebra. Okay, diagram chase is very, how to say, very safe. What do I mean by very safe? Bring you security, 安全感。你可以去追，你试一下做 diagram chase 的 proof，就是你就一步啊，安全感哈，因为 you cannot go wrong，已经写好给你了啊。You can't go wrong. Okay, yeah. 所以你就是乖乖的 check 就对了。Okay, and then 还有什么我要讨论哈？哦，maybe tell you what's the map between them。我不会 proof 给你看，要不要 proof 吗？要 proof 吗？还是不要了？还是不要了？你自己看了。但是我告诉你是什么 map。Okay, and then 那个为什么是 isomorphism 就用到我们之前全部教过的东西。Okay, so what's this map here? So meaning delta simplex and simplex, you need to give a singular simplex. Okay, give you a delta simplex, you need to give a singular simplex. So what is it? Very easy. It is the characteristic map. That's it. Okay, because you need to put your delta x in your x, right? When you do the delta complex, then you just send it to that characteristic map. 怎样连 So the idea is this. Delta the simplicial homology 是算那个 homology of 那些 singular homology 就是在算这些连的 map 的 homology，就这样吧。 它故事就这样了。但是当然你要 check 就有很多 technical 的东西这样去 check。OK， 有问题吗？这样就有问题吗？Okay, so a delta map, a delta complex will determine a frequency map， 就是说你怎么把这个 delta m 连你的 x 里面，那这就是一个 singular simplex， 这个就是 singular simplex。对对，另外一个可能没有 care about 那个 map， 但是已经有那个 map 在了，因为不然的话，你怎样去形容？对，不然你怎样形容你是用这个 delta n 做什么的？其实有 map 在那边的，但是我们 ignore 掉那个 part， 但是我们只看那个 part 的话，也可以算东西出来，这就是很特别的地方。我们也可以只看它，特别吗？你觉得？一个是看物体本身，一个是看物体怎么粘。但是什么？就是一个是看物体本身，一个是物体怎么粘，但是他们没有 loss information。为什么？你在看物体本身的时候，你也要知道它怎么粘啊。那你要看它怎么粘的时候，你要看你在粘什么啊，对不对？所以没有 no information loss，actually， 神奇吗？神奇啊！
没有，我就觉得一样东西。
再看它一样，不然你只看它一样，你就少了这份那个它的啊，你要看它不一样先才看它一样。你要从它一样看出它不一样，再从它不一样看出它一样，那还是真的一样。在讲什么啦 ？I mean like， 呀啦 ，I mean like， 他们的 focus 不一样嘛，一个是看 map， 一个是看 delta simplex， 一个是看 singular simplex， 不一样啊，两个字都不一样，是不是？但是这两个字 encode 的 information 是一样的，什么名字不一样？
A 月和谁月头这两个字
对啊，也不一样啊，
这样找。
对啊，就不一样，对啊。
然后可以讲一种想法，
想要
看我老妈看我是不是一样？
看你老妈跟看你是不是一样？为什么？我那你知道你老妈跟你一不一样？